In this next section, section 2.5, we'll be talking a lot about graphs of functions. And I guess the idea is hopefully we can find a way to tweak an old graph to graph a new graph instead of having to plug in the x values over and over and over every time we want to graph a new function. So that's the idea behind this section, section 2.5, called transformations of functions. Okay, let's see. What do they have to say? Their little intro here. Movies and mathematics. So they're trying to make math more exciting by tying it to movies, but you know, it's a stretch. So let's see. They say, have you ever seen special effects in a movie where a person or object was continuously transformed into something different? Yeah, I guess what I can think of is like a werewolf, I guess. That's yeah, okay. This is called morphing. Okay, interesting. In mathematics, we can use transformations of a known graph to graph a function with a similar equation. This is achieved through horizontal and vertical shifts, reflections, and stretching and shrinking of the known graph. Okay. And I think, you know, when we do the first couple examples, you'll recognize we've seen this a little bit in a previous section. Yeah, where we take one function and we add something at the end or subtract something at the end, and then that moves the graph up or down, something like that. That's an example of a transformation. But first, what I wanted to do is point out that there are, I think, 4 basic graphs that we should kind of have memorized at this point. I mean, well, after this point. I don't expect you to have seen all 4 of these necessarily recently or have them memorized, but it's a good idea to memorize them now. So on the very left here, I've drawn a little graph of a parabola. So the basic parabola is y equals x squared. It's just kind of like a U shape where the bottom of the U is on the origin. And the next one we have here is the graph of y equals x cubed. Notice the right side of it, the one that's on the right side of the y-axis, this part that I'm trying to make darker, it looks a lot like the right side of the parabola. So it's like almost like a half U. It's just that the left side of the parabola it's almost like it fell down. You know, like there was a hinge at the origin and the left side fell down. Okay, and then the third graph that we should kind of have to memorize at this point is the graph of the absolute value of x. This one I think we've seen in a previous section just really briefly, but the graph is pretty much just a V shape where it starts at the origin. Sorry, I kind of erased a little bit there, but yeah, but it makes a 45-degree angle with the x-axis. It's kind of an easy way to remember it. Let's see, and then the very last one that's probably a good one to memorize is this guy, the square root of x. So the square root of x, it just kind of looks like, to me, I don't know why I always think of it, looks like someone shot like a rocket off at a 45-degree angle, you know? At first the rocket goes in the 45-degree angle and then it kind of, I don't know, comes back down to earth, you know? Except this one actually does, it keeps increasing forever. It looks like it's flattening out there, but it actually keeps increasing forever, slowly, slowly. But yeah, those ones, we'll be taking those basic graphs and we'll be tweaking them a little bit. So it's good to have those memorized, because all we're going to do is take those graphs and, you know, shift them up or down or left or right, or we'll reflect them across the x-axis or reflect them across the y-axis. So that's what this section's all about. And then when to recognize which direction do you move the graph, when, and all that. So okay, but first we're going to do a little, I guess this is just kind of to see if we're awake, this first example. I want to be able to recognize the graphs of common functions. Okay, so first it says, the graphs of the standard quadratic function f of x equals x squared and the absolute value function, absolute value of x, have the same symmetry. That's true or false. So I guess they're not telling us it does. They're asking us if it does. So let's see, maybe we'll bring those graphs a little lower so we can see them. So let's see, we'll graph x squared and we'll graph the absolute value and see if they have the same kind of symmetry. So remember, the types of symmetry we have are, there's x-axis symmetry, where the top and the bottom of the graph are the same. It's like, you know, if there was a mirror on the x-axis, then the top would be a perfect reflection of the bottom, and vice versa. And then there's a y-axis symmetry, it's the same kind of thing, except there's a mirror on the y-axis. And then there's origin symmetry, which means you can rotate the graph 180 degrees and it should be the same graph as you started with. So these guys, I imagine, okay, I'm going to check for, I guess, x-axis symmetry, just only because that's the first one we mentioned. Symmetry let's see, the first one, the left one that I graphed, does not have x-axis symmetry. Because if I imagine trying to reflect this guy below the x-axis, I don't see a reflection of it on the bottom. You know, there'd be some brand new piece to it. So, and that's the same as the other graph, the graph of the absolute value. If I were to reflect that graph across the x-axis, there would be this portion down here that looks like this. But that wasn't part of the graph to begin with. So that one is a no. Let's see about y-axis symmetry. Maybe. Symmetry. Alright, that would mean that the left side of the y-axis and the right side of the y-axis are perfect mirror images of each other. So if I were to take, for example, this left side and reflect it, that would be a perfect mirror image on the right side. Same thing with the absolute value graph. So I think they both do have y-axis symmetry, so I'm going to say yes. And that kind of goes for both of those guys. And then the last one, origin symmetry. Symmetry. That one would be a no for both, because if you were to rotate, I guess the left graph, for example, if you were to rotate it 180 degrees, it would still look exactly like the one we just drew down there. And that, there's, like I said, that it would have to, you'd have to be able to rotate it 180 degrees, and it would look like the same graph you started with, which it doesn't. Now it's upside down. Same thing with the absolute value graph. It's an upward V, but if I were to rotate it 180 degrees, it would become a downward V. And that doesn't look the same as it did. So I'd say the answer to the question they asked is true. They do have the same type of symmetry. They have y-axis symmetry, but no x-axis and no origin. Let's see, and then the second part of this part, problem 1, part B, says, true or false, the graphs of the identity function f of x equals x. Okay, that one we didn't draw at the top of the page. Let me see. That one I can think about. Remember that anytime you want to graph a function, you can always replace f of x with y, and then that kind of, I don't know, that kind of helps me to kind of wrap my mind around it. But if it's y equals x, that's just the graph of a line where the y-intercept is 0 because there's no b. You know, it's supposed to be mx plus b. M is 1 because that's the coefficient of x. So I'll start at the y-intercept of 0, and then I'll rise 1, run 1. So it looks like that. So it's like a diagonal line that goes through the origin and makes a perfect 45-degree angle with the positive x-axis. Alright, that one, and they want us to compare it to which one? Oh, the cubic function x cubed. Okay, that one we did have above. So I don't know, it's up to you if you want to add this graph, the graph of f of x equals x or y equals x. You can add that to your kind of repertoire up here of the graphs that we're supposed to memorize. Or, like I said, it's just, to me, I think that's just too much to memorize. I already know how to graph a line, so I can always kind of reinvent the wheel every time if I don't feel like memorizing that guy. But let's see, g of x equals x cubed. That's one I should memorize, so there's him. Do they have the same type of symmetry? Let me see. First, does this guy have x-axis symmetry? No. Neither of these have x-axis symmetry. X-axis symmetry, because if I were to reflect either of them across the x-axis, they look like different graphs. What about y-axis symmetry? No, for the same reason. No y-axis symmetry, and that goes for both of them. Because if you try to reflect their graphs across the y-axis, it would be a different graph. But yes to origin symmetry. Origin symmetry. Because if you were to rotate, for example, the line y equals x, if you were to rotate that 180 degrees, it would land right on top of itself. It's just kind of like the top right portion would land where the bottom left portion is, and vice versa. And similarly for the y equals x cubed graph. The top right portion would rotate and land right where the bottom left portion is, and vice versa. So the answer is true for this one as well. They both have origin symmetry, but they don't have any other kind of symmetry. Alright, well now what do they want us to do? So this example, use the graph of x squared. Okay, we're supposed to have that memorized. So maybe I'll graph that guy first. He goes something like this. And you know, you're just graphing kind of a rough sketch. It doesn't have to be perfect. This guy right here. Yeah, if your little parabola shape looks a little wider or a little narrower than mine, that's fine. I think this is more just to practice knowing what this -2 does to the graph. We've actually seen this in, what was it? I can't remember if it was the last section or the section before. But what we've kind of come to realize is that if you take one of the basic functions, like x squared, for example, and you add or subtract something at the end, that moves the graph up or down. So if I were to take a function and add something at the end, so k, I'm just kind of trying to keep it general, but it's supposed to be a number, that would moves the graph up k units. But if it's a minus sign, like it's a basic function that we've memorized, the ones that we drew at the top of this page, and then we subtract a number at the end of it, that moves it down that many units. Moves the graph down k units. Okay. Just so we have that, you know, that was a couple sections back maybe. So that means that this minus 2 is going to move the graph downward 2 units. So picture the green U shape that I've already drawn, the graph of x squared. Imagine if I move it down 2 units, then instead of starting at the origin, it'll start at -2. But then it'll kind of have the same shape. So I'm going to try to... Okay, I'm not a very good artist, so I'm trying to make that look like the same graph, but it doesn't really look like it. Oh well. But don't worry, I'll keep that in mind, you know, as I'm grading your guys' tests and quizzes and stuff. If you don't have a good artistic eye, hey, that's okay. It's a math class, you know. That's why sometimes if you think you're not a very good grapher or you're not really good at drawing, you can always just say something like write it there, say graph moves down 2 units, you know, in case you're worried. Okay, whoever's grading this test or quiz might not know what the heck I'm trying to do because I'm such a terrible artist. Hey, well, you kind of covered your rear end by putting what you're trying to do here. So remember, I always try to do that when I was a student because, I don't know, I was always paranoid someone couldn't figure out what the heck I'm doing. Alright, so hopefully that's kind of a good little review of what we saw a section or two back. Now we're moving on to the next type of transformation, because we've just talked about vertical transformations, they're called. Maybe I'll try to title this little area here, just so we know. Vertical transformation. Yeah, because this will be the time where you would move a graph up or down. But now we're going to talk about horizontal transformations. Let's see. So it looks funny when you see it in this highlighted area. It says the graph of f of x plus k is the graph of f of x shifted left k units, okay. And the graph of f of x minus k is the graph of f of x shifted right k units. So if you're, you know, I might be thinking, especially if I haven't seen this before or it's been a long time, doesn't this look exactly the same as what we just did? But what we just did was shift up and down. But now all of a sudden they're saying left and right. Well, the difference is, in the last one we did, notice, let me see, just to highlight what we were working with. Notice that the -2 is just kind of at the end of the function. Because the interesting part of this function is the square, you know, it's just taking an x and squaring it. But the 2 that we subtracted was not involved in the square. It was like, okay, x was squared, and then we subtracted 2 kind of toward the end. But now the type of thing we're looking at is whatever's interesting about the function, whether it be x is being squared, x is being cubed, x has a square root, x has absolute value, the number adding or subtracting is involved in that action. You know, it's inside the square, it's inside the cube, it's inside the square root, it's inside the absolute value. So that's the difference. That's if you're not, you know, familiar with that, that might not be a bad idea to point out. The horizontal transformations have a number inside the function instead of at the end of the function. Horizontal transformations have a number adding or subtracting inside the function. Whereas vertical had it just kind of sitting at the end. So that's how I would know when I look at this function they're giving me g of x equals the square root of x minus 4. So if it was the square root of x and then minus 4 and the 4 was not inside the square root, then it would be a vertical transformation like we just saw. I would move the graph down 4 units. But since the 4 looks like it's inside the square root, that's how I know, that I'm going to be moving it left or right. So probably what's a good idea is to think about the original graph, the square root of x, and just kind of try to think about how that guy looks. He looks something like this. y equals square root of x, and then I'll think about which direction that's going to move now that I want to graph g of x. So yeah, that was f of x. I guess I should call it that. And then g of x, it looks like there's a -4 inside, and that looks more like this guy here. It's x minus something, and it says when it looks like that, you're moving it to the right. So I'm going to move the graph to the right 4 units. Right, oops. What can I spell right? Hello. Right 4 units. So we'll go 1, 2, 3, 4, starting here now, and then the same shape. Something like that. That'll be our g of x equals square root of x minus 4. The one thing to point out is that with the vertical transformations that we just saw in the previous example, when you have a plus, it's like, say, like the one we did, what was it? That one had a minus. What was it? Yeah, x squared minus 2. It's kind of what I would think to do. Like if you had a -2, would you think to go up or down? Oh, okay, I would think to go down because it's a negative and downward is the negative direction. And if it's a plus, you go upward. So it kind of goes with your instincts, but these horizontal transformations are the opposite of what you would think. So, you know, we had a minus, and if we're doing a horizontal transformation, we're either going left or right. I would think a minus would move you left because that's the negative direction, but you're actually moving right. And then the same thing with the plus. I would think a plus would move you right because that's the positive direction, but you're actually moving left. So that's the bad thing. And with horizontal transformations, you're kind of going against your instincts. It's just kind of something you have to memorize, unfortunately. Okay, now we'll try this next one. This one has an absolute value. So maybe I'll try to graph f of x equals the square root of x first, and then we'll work on what they want us to graph. So use the graph of that guy. Okay, that guy's a V-shape, something like this, you know. So there's our normal absolute value function. He's cute. And then I gotta think about which direction would this 2 move it. It's either moving 2 units up, down, left, or right. But first of all, the 2 is inside the function. 2 is inside the function, and that's because it's inside the absolute value. It's not like 2 is adding at the end of the function. It's not like absolute value of x plus 2. Now that would be a vertical transformation. So this one, since the 2 is inside the function, it's a horizontal transformation. So I know it's either moving left or right. That's kind of, I'm narrowing it down now. Transformation. All right, then I have to remember which way, or which way does a positive 2 move it? Well, like we said before, horizontal transformations move the opposite way of what you would think. I would think if I'm moving either left or right and I have a positive 2, right is the positive direction. So that would be the way to go, but it's actually left. So I'm going to go left 2 units. Alright, so imagine this V shape going left 2 units. Then it would start at x equals -2 instead of x equals 0. And then it would make its V shape. So this guy would be the one we want. G of x equals absolute value x plus 2. There we go. And like I said, these graphs don't have to be perfect. They just want you to know when to move the graph up, down, left, or right is pretty much it. But if you don't have a perfect V shape or a perfect parabola or perfect whatever, it's not a big deal. Don't worry too much about it, please. Okay. Now we're going to talk about reflections. So sometimes when you involve a negative in one of the basic functions, like we see here, put a negative in front of an absolute value, that's going to reflect the graph across either the x-axis or the y-axis, so we have to think about it. So I kind of explain why here, why is it actually an x-axis reflection? So let's see, so if you have, well, let's talk about y in a second, but I'm just going to write it down here so we have it sitting here. Let's see, a negative in front of the function means an x-axis reflection. Alright, so that's what we're supposed to take away from this example, but they kind of explain why here. The graph of g is a reflection of the graph of f about the x-axis because, yeah, it's all you're doing is throwing a negative in front of a regular function that we're used to. So basically what we're doing is replacing each y-coordinate with its opposite. Is what's going on. So that means since they just chose these points are on the absolute value graph. That means we're changing all the y values to their opposite signs, which if you were to plot those new points with negative y values, then it would be an upside down v instead of a right side up v. So like, yeah, they kind of have it all. It's all in black and white, so it's kind of hard to see. But this guy is f of x equals absolute value of x. But if you were to throw a negative sign in front of that, let's see, and it would be this upside down v that's going downward. So that guy would be your reflection. Yeah, so that's, you know, just yet another thing to memorize. If you take one of our basic functions that we drew at the very top of this section and you put a negative in front of it, all you have to do is take the original graph and reflect it across the x-axis, and that'll be the new graph. So how about we'll practice that with this guy here, this part 4b. Use the graph of f of x equals x cubed. Okay, first thing I would do when I do these problems is just try to remember what that graph looks like. Looks something like this. You know, that's a pretty good looking graph, I guess. All right, but I want to throw a negative in front of it, which means I'm going to reflect that guy across the what's it called? The x-axis. Reflect across the x-axis. Okay. And if you're not familiar with reflecting across the x-axis, it's kind of, I don't know, there's kind of an art to it, or it kind of takes some thought. But what I do usually is I'll do one portion at a time, especially x cubed, his graph, half of it is above the x-axis, half of it's below. So I might, for example, I might focus on the top half here, or the right part. The right portion is above the x-axis, but if he reflected across the x-axis, he'd be downward like that. So that kind of looks like a reflection. And then I might focus on the the left portion. He's down below the x-axis, so if I were to reflect him across the x-axis, he'd go up to the top. So that must be the new one we want. G of x equals negative x cubed. Yeah. So it's not too bad. Yeah, I think actually graphing these and reflecting and translating and all the things they're wanting us to do, it's not that bad. What's bad is having to memorize when to do it. You know, if there's a plus sign here, you got to do it then, and you move it left, right, or up or down, and if there's a negative here, you yeah. It's a lot of, anyway, it's a lot to memorize. That's the bad thing. All right, so now I'm looking at the next example. It looks like they're doing something similar. But this time, notice they're putting a negative inside the function instead of outside. So I might point that out. If that's something new to you, then that might be worth making a note of. Now, the negative is inside the function, whereas the examples we just saw, the negative was just in the very front of the function. It wasn't involved in the square or the cube or the square root or the yada yada yada. And this example actually, we don't have a basic graph drawn out at the very top of this page for the cube root of x. You know, that one you don't see too often, but maybe it's worth drawing it just for the rare times you do see it. So let me go back to the very beginning and draw him. Let me see. Yeah, that one you won't see very often, but hey, at least we'll have them all in one place. Let me get some space over here for this last guy. Let's see, what color haven't we used yet? Orange, I guess? Whatever. Yeah, y equals the cube root of x, as opposed to the square root of x, is actually the right side looks a lot like the square root. But then there's a left side also. He's kind of like, yeah, it almost looks like the cube, right? Like, looks like this guy. Except he's along, and almost as if you rotated that 90 degrees or something. That's the guy. That's how I remember it. I remember it looks like the square root graph, except there's an extra portion on the bottom left quadrant. Alright, so let me see if I can bring that information down to the example we're working on here. Yeah, they've actually drawn it for us, but it's really hard to tell what the hell they're doing. This was the original guy, f. F is the cube root of x. So that's just the regular cube root of x graph. But this time, like we said, now the negative is inside the function, so it is a y-axis reflection. Because anytime there's something going on inside the function, whether it be you're adding something at the end, or you're adding something inside the function, subtracting, or you're putting a negative in there, like we see in this example, it's going to be some kind of horizontal transformation or horizontal change. Because imagine if you reflect something across the y-axis, that's going to change it horizontally, but not vertically. So anytime there's a change inside the function, that's going to be a horizontal change to the graph. Yeah, let me try to find a color that's totally different. I guess like blue. There we go. So h of x would be this guy. That's the reflection of the orange graph f of x across the y-axis. H of x is cube root of negative x. So it's like, yeah, the blue graph is a reflection across the y-axis of the orange graph. The blue, you don't have to write this. This is just in my brain. This is what I'm thinking. The blue graph is a reflection of the orange graph across the y-axis. There we go. Alright, and then do some more explaining of why, but, you know, basically what you're going to do is try to memorize that if I see a negative inside my function, I'm going to reflect the original basic graph function across the y-axis. Okay, now this next example is kind of wild. Oh, I don't know about wild. As wild as math gets. So giving us a graph, let's see, it's kind of like, looks like a bunch of lines sewn together. Almost like those piecewise functions we saw a couple sections back, where it was a couple lines Frankenstein together. Just said use this graph. They're saying this is f of x. We don't really know what the equation of the function is. It's not like, oh, I know that's a square root graph or it's absolute value graph. They're just saying here's this generic looking graph, and then they want us to graph the function that would become, or well, what the function would become if we put a negative inside of it. So basically, what they want us to do is to reflect that across the y-axis. Reflect across the y-axis. Okay, that's not very easy to do because, first of all, I'm not familiar with this graph. It's not one of the basic ones that I'm supposed to memorize. So I think for these types, what helps is to kind of take note of the points that are on the graph. You notice that they've kind of pointed out some points. There's 4, 0. I'm kind of looking from right to left here. 4, 0, 2, 2, 0, 0. And they've got negative 4, 0, negative 2, negative 2. Those are kind of all the points there, but what we can do is think about, okay, if all those points reflected across the y-axis, what's changing here? Well, 4, 0, if I reflected that guy across the y-axis, he would become negative 4, 0. Because that's the point that's on the very opposite side of the y-axis, and then 2, 2 would become negative 2, 2. Let's see, and I can kind of maybe use a different color, like blue. So this would be the new point for 4, 0. 2, 2 would move to negative 2, 2, so right here. And then what else? Let's see. So 0, 0. That one, though, it's right on the y-axis, so it doesn't move. It's only something on the left of the y-axis moves to the right side. Something on the right side moves to the left. But anything on the y-axis isn't moving anywhere. And then there's negative 4, 0. That guy, he wasn't on the left side, but now he's moving to the right side. He'll move to 4, 0. So it's like the points 4, 0 and negative 4, 0 go switching, they move around. And then the point negative 2, where is he? On the graph, let me see, he's here. Just imagine him moving to the opposite side of the y-axis. He'd move right here. And that point is positive 2, negative 2. I don't know why this one's in a different color. Don't worry about that. Okay. So pretty much what we did was, I guess, we came up with these points by visualizing where these values would move. But what happens is you're just changing the sign of the x value. Change the sign, from negative to positive, positive to negative of the x value. Yeah, and then now I can just plot those points. I have negative 4, 0, okay, that guy. And then negative 2, 2, this guy. And 0, 0, okay, good looking guy. Positive 4, 0, and positive 2, negative 2. And then this was just a bunch of line segments, so I can go ahead and connect these dots like so. That looks like it could be a reflection across the y-axis, Although the graph I just drew, the green one looks a little smaller. It's only because the x and y coordinate system is kind of scaled differently on this one. I think, yeah, the coordinates are closer together on this coordinate system than the top one. But yeah, that'd be a way to go. I think you won't see something like that too often. That's a little more rare. Alright, then one of the last objectives we have is they want us to use, let's see, first of all, the graph of absolute value. So we have that guy memorized. They have already graphed it here, down here in the green. That's the graph of absolute value. So value of x, okay. To graph. Alright, now they're introducing something new. We haven't seen this before where we're multiplying. Oh, so the old function absolute value, we're going to multiply it by 2. So so far we've seen adding and subtracting numbers to the function or giving it a negative sign, but we haven't seen multiplying. Okay, so they've kind of given us an outline of what to do. The graph of g, which is the result of me multiplying the original function by 2, is obtained by vertically stretching the graph, and that's because I'm multiplying it by 2, so every y-coordinate is twice as tall as it was before. Okay, so I guess imagine if you're vertically stretching, imagine you stretch something upward. That's kind of going to make it narrower, you know? It kind of makes sense. So that's why this graph looks like the absolute value, but it became narrower. Let's see, and then it won't always become narrower though, so I'm going to make a little note down here just so we know when it'll become narrower. Let's see, if I want to just draw it or write it as g of x equals k times f of x. So, you know, k being the 2 in this example, 2 here. But it could be something else, it just depends on the example. But here we have a 2. If I should say something like in the graph of g of x equals if k is greater than 1, it's a vertical stretch, like what they said. Because the number we had was a 2, which is greater than 1. But if k is less than 1, so it's like a fraction or a decimal, you know, if it's a half or a third or 2/5 or something like that, or 0.5 or whatever, it's a vertical shrinking. A vertical shrink, which if you kind of imagine, what if I were to shrink something vertically? Like imagine I squished it from above, it would kind of get wider. So I might, if you want, I'm going to make a note of that. Wider. This is narrower. That's basically how the graph will look. So yeah, when you have a function and it's multiplied by a number, what you have to do is look at that number and say, okay, is it bigger than 1? If it is, then it's going to be narrower. If it's smaller than 1, then it's going to be wider. So this example 5b here, it has a number in front of the x cubed. So maybe I'll get ready here. I got an x cubed. Let me see. I got to dig down in my memory and remember what x cubed's graph looks like. He looks like this. X cubed. But now I'd like to know what happens when I have a half in front. Well, from the note we just made, half is our k value. That's less than 1. So it should be a vertical shrink, which means it should get wider. So I just imagine this graph a little wider. And like I said before, we're kind of just, they just want you to know that it's getting wider or narrower or moving left or right or reflecting. If yours is a little wider than mine, the green one, or it's a little narrower, that's fine. You know, basically as long as your new graph is wider than your old graph, I don't know, I wouldn't worry about just how wide it is and all that. That we'll get to later, more details on this guy. Alright, so this is a lot to memorize, I know. That's why I was never a fan of this section of the book. I don't like it. It's too much to remember. Alright, now they're getting a little too wild here. Now they're going back to those types of functions where it's not one of the basic graphs that we're supposed to have memorized. It's just this random little one that has a bunch of line segments all shoved together. So they say, use the graph of f shown below to graph each function. So then first they want us to graph f of 2 times x. So since that shows me that k is 2, and I'm supposed to compare that to 1 to see whether I stretch it or shrink it. K is greater than 1, so it should be a vertical stretch. Let me see. Stretch, yeah. That means that since k is 2 and it's a vertical stretch, the y values of any points that are on the graph are multiplied by 2. By 2. Which kind of makes sense now that it stretches, because if all of a sudden your points are doubling, the y values are doubling, they're getting really tall or they're going really low. So okay, let's see. Let's see. So these points, let's say for example, maybe I'll highlight them because they already have the graph ready for us. So here's this guy. That one though, the point -2, 0 has a y value of 0. If you double 0, you know, you're still at 0. So that didn't really do a whole lot. Ah, you know what? I'm sorry, you guys. Let me erase this real quick. I'm sorry. Let me see. I'm making the classic mistake that a lot of students make. Or maybe you seeing me make this mistake will make you not make it. Hopefully. This last objective here, objective 6, is different than the previous one. Because this one, let's see, I'm going to try to use a new color here. This one, notice that we were doubling the function. The 2, though, was multiplied in front of the absolute value of x. So it was outside the function. So it's here, these ones in objective 5, you're multiplying a number outside the function. So it's different. It would be, I guess it'd be different if I had 2 inside the absolute value instead of outside being multiplied. So that's what we're given now. I'm sorry, I screwed up. Now they're giving us the 2 is inside the function. 2 is inside the function f. So it's some kind of horizontal change. That's what we've found out so far, is that if a number is adding or subtracting or multiplying or whatever inside the function, that's a horizontal change. If it's outside the function, that's a vertical change. A horizontal change, which means x values are changing. X values change. Not the y values. I'm sorry, I'm being silly. Okay. So, and then, just like we've seen before, any kind of horizontal change, it kind of goes against your instincts. Vertical changes are exactly what you would think would happen. You know, like in the previous example, I had a 2 multiplying by the function. So the function got taller and the y values doubled, which kind of makes sense, but when it's horizontal changes, it's always the opposite of what you would think. Instead of multiplying x values by 2, I'd actually divide them by 2. So that's what I would say. If you learn anything from this section, it's that horizontal changes are opposite of what you would think, and vertical changes are exactly what you think. Basically go against your instincts. Your instincts. I would think that multiplying by 2 would mean I'll multiply the x values by 2, but I actually do the opposite and divide. I will need to divide all x values by 2. So all the points that we were given in the original graph, okay, now I can go back to where I was highlighting. The highlighted point, -2, 0. If I were to do like I described here, divide all x values by 2. What if I divide the x value of that point, that highlighted point, -2, 0, by 2? Then I would get a -1, 0. So I've plotted that point down here. Let me do that to the next point here, 0, 3. If I were to divide that x value 0 by 2, it's not going to change because 0 divided by 2 is still 0. That's why the point 0, 3 has remained unchanged. And then we have the point 2, 0. If I divide that x value by 2, I've got 1. That's why the point 1, 0 is on the graph of the new function. And then the next point I see is 4, -3. If I divide the x value 4 by 2, I get 2. But all the y values are remaining unchanged because this is purely a horizontal change, not a vertical change. And the last point is 6, 0. If I were to divide that x value, 6, by 2, I'll get 3, 0. So that's kind of how to go about these guys, I guess. Is to take the points, and if it's a vertical change, you do what you think you would do. I would multiply in this case. But, yeah, it's the opposite of what you would think. Wonderful. So here's another one. So this is a 1/2 is multiplied. That's kind of what I'm thinking in my head. Inside the function. So it's a horizontal change. Okay. And so what my instinct would be is, okay, there's a 1/2 multiplied in there, and it's a horizontal change. Horizontal changes happen to x values. So I know for sure something's happening to the x values because that's what happens in horizontal changes. But I would think I would multiply by 1/2 because that's what's happening you know, right here in the function. X is multiplied by a half, but I'm going to do the opposite because it's a horizontal thing. Horizontal is always the opposite of what you would think. Are divided by a half. And that should do it. But notice that they've actually, the way they've written it here in the typing that they've written is, they just simplified it. They're actually going to multiply each x coordinate by 2, which seems like it's different, but if you think about, if you divide something by a half, you know, I don't know, like 4 for example, what if I divide 4 by a half? Well, remember then you have to flip and multiply, so I do 4 times the reciprocal of that, which is 2 over 1. So you pretty much end up multiplying by 2. So what they've written here is just a simplification of what we've said. We said divide the x coordinates by a half, but they're saying, well, that's the same thing as multiplying by 2. Or multiply x coordinates by 2. Okay, so if we were to go up and look at all these points, let me maybe highlight them in a different color. So this guy, for example, negative 2, 0, I'm doubling that x value. It should be a negative 4 instead of a negative 2. This point here, 0, 3, the x coordinate is 0, so if I double it, it's not really doing much. If I double this x coordinate, though, it's a 2, I'm getting 4. If I double this x coordinate, which is 4, I'm getting 8. If I double this x coordinate, which is 6, I'll get 12. So that's why you see the graph really stretched out horizontally here, because you're doubling all your x values. So I'm sorry. There's so much to memorize in this section. It really annoys me, but it's one of those things you just have to get past. Ugh. But at a certain point in math, if it makes you feel better, is you'll be allowed to use a graphing calculator. Because I guess you've already proven yourself, like, oh, I've passed all the tests where I had to memorize what the graphs look like. Now that I've done that, all right, now I can use a graphing calculator, and those calculators will graph anything for you. So that way you don't have to really worry about memorizing this stuff forever. As long as you memorize it for a while, that should be enough. All right. Anyways, so let's try one of these on our own. They kind of helped us in the last one, but now we can try it on our own. So I've given us a graph, looks kind of similar to the last one, and I've kind of specified the points that are on it, so that'll help. But now they want us to do this horizontal change where we're multiplying inside the function by 3. But okay, that's my first thought is, okay, I want to make sure I know that this is a horizontal change because it's inside the function. The 3 is inside the function. 3 is inside f. So since it's a horizontal change, that's going to be, the x values are changing because that's what happens, you know, as you move things horizontally. And it's the opposite of what I would think. So since there's a 3 multiplying, I'm actually going to do the opposite and divide by 3. Are divided by 3. So let me see. I'm going to take all these points. It's not going to be pretty, huh? So for example, negative 4, 0. What if I divide that x value by 3? That'll be negative 4 thirds 0. So that's my new point. And then what about the next point? Negative 2, negative 2. If I were to divide that x value by 3, I'll get negative 2 thirds negative 2. But notice the y values aren't changing like we mentioned before. And then we have the point 0, 0. If I were to divide that x value by 3, I'd still get 0, because dividing 0 by 3 doesn't change it. If I take the next x value from the point 2, 2, and I divide it by 3, I get 2 thirds 2, because the y value is not changing. And then the last point, 4, 0. If I divide that x value by 3, I'll get 4 thirds 0. There we go. Now my job is just to plot those points, and then I'll connect the dots, and I should be good. And this you can kind of, I don't know, guesstimate. Negative 4 thirds is a little further out than negative 1, because that's negative 1 and 1/3. So I'll go negative 1 and 1/3, maybe here or something like that. Somewhere around there. And then negative 2 thirds, that's not quite to negative 1, and I'm going down 2 for the next point. And then I've got 0, 0, that didn't change. And then 2 thirds, that's not quite to 1, but then up 2, there he is. Somewhere around there. And then the last guy is 4 thirds, comma 0. Let's see, 4 thirds, again, that's 1 1/3, so that would be just past 1 on the x-axis. I'll just connect those dots. So that little zigzag shape got really narrow. Yeah, it's just as tall as it used to be. Notice that the first zigzag that they drew, f of x, up here, it goes up as high as +2 on the y-axis and as low as -2. So ours still does that on this one. It's just that it's really narrow. It only goes as far as -4/3 on the left side and +4/3 on the right side. All right. So let's try this next one. Actually, this looks just like this last one. Wait, what was it? Yeah, actually, I realized that this looks just like this guy. F of a half of x. And that's what we have here. So how about, just for fun to change it, well, let's put a 4 there, make it a 4th. Is that okay? Just so we have our own new problem instead of doing the exact same one we saw before. Okay. Let's try that guy. So, I'm kind of, in my mind, I'm going through the whole thing again. There's a 4th multiplied inside the function. So it says inside the function. That means it's going to be some kind of horizontal change. Okay. And then we said horizontal changes, okay, those occur to the x values. Vertical changes occur to the y values. And since it's a horizontal change, I'm going to do exactly the opposite of what I want to do. It looks like there's a 4th multiplied by x, but I'm going to do the opposite of that. Divide by a 4th. By 1/4. Alright. Then if I'm being clever, like in the previous example, I can say, you know what? Dividing by a 4th is the same as multiplying by 4. Because again, like we said before, if you divide by a 4th, you'd have to flip and multiply by the reciprocal, which is 4/1, or 4. So we'll just say, let's multiply by 4. Alright, so I'm going to take all the points from the very first graph, because that's the one we're supposed to base everything off of, and quadruple their x values. Let's see, the first point, well, the very leftmost point is -4, 0. I'm going to multiply that x value by 4 and get -16, 0. And then the next point from the left on is -2, -2. So if I quadruple that x value, I'll get -8. But like we said before, these y values aren't changing because this is purely a horizontal change. And let's see, the third point was 0, 0, right? Yeah. And if I multiply 0 by 4, it's not going to change, so he stays the same. And let's see, what do we have next? Then the next point is +2, +2. Sorry, +2, +2. If I multiply that x value by 4, I'll get 8. And then the last point, if I remember right, was 4, 0. If I multiply the x value by 4. Yeah, by 4, sorry, I'll get 16. Alright, I don't know if I have room for all that. This only goes up to 10. Oh, well, I might have to extend it here. Let's see. Let me extend this. 9, 10, 11, 12, 13, 14, 15, 16. Let's just say there's 16. And I'll go off this direction. 10, 11, 12, 13, 14, 15, 16. Sorry. That kind of went off, way off, further than I was supposed to go, but oh well. Okay, let's plot some points here. The first one was -16, 0. What was the second point? -8, -2, so he's over here. And then the next point is 0, 0, okay, the origin. Now we have +8 to up to, so there he is, here. And then 16, 0, right on the x-axis. Alright, then I'm supposed to connect the dots, and it's supposed to be, you know, like a zigzaggy pattern, so I'm trying to make them straight lines. Wait, did I miss somebody? Oh, there he is. I forgot about this little guy. There we go. Alright. So that zigzag pattern from the very first graph that they gave us, this guy, it really widened out from this one. So definitely if you were to multiply a fraction inside a function, it makes it a wider, stretched out graph. Stretched out in the horizontal direction. Okay. Our very last objective, finally. We're going to keep this video under an hour, I promise. So now it says, okay, use the graph of da-da-da-da-da. Alright, now we're kind of combining all kinds of transformations in one function. So we got to really think about this. I might have to take note. We have a -1 inside the function. I'm kind of thinking of from inside to outside, looking at these. So I got to remember, what does that do? That shifts the graph right? Yeah. Shifts the graph to the right. Okay, so that's one thing. And then I know that the +3, well, I guess if I focus from inside to outside, this guy looks like he's coming next. The 2 multiplied let's see, the 2's outside the function because it's not inside with the square. You know, the 2's not being squared, so it's outside the function. That means it's going to be some kind of vertical change. So it's a vertical stretch. That's what we talked about before. If the number is bigger than 1, it stretches vertically. If the number is smaller than 1, it shrinks vertically. Okay, and then the one we haven't talked about yet is the +3. I guess I ran out of room for that. Since the +3 is outside the function, it's just adding at the end. That's the very first thing we talked about. That's going to be a vertical shift. Shift the graph up 3. So if you were to put all those together, let's see, this like the basic parabola looks like this down here. So what they've done is they've put all those together. They've, let's see, taken that, they've moved the graph to the right 1 like we talked about, so it's going this way. It's shifted up 3, and it got narrower or vertically stretched. That looks good. And they were very, what's really smart of them is that they took points that were on the original graph. These are on the graph of y equals x squared. And they've done all those things to them. So first, what did they do? What did we mention first? -1 inside the function, it shifts the graph right. But if you think about what is, if I shift a point to the right, that adds 1 to the x value, you know? If that makes sense. Because like, yeah, let's say here's blah, blah, blah. Okay, here. And then I have a point here. If I move it to the right, what did that? That didn't change the y value because I'm not going up or down. It just changed the x value +1. So they're adding 1 to the x values. Add 1 to x values. So that takes care of the first thing we mentioned, this guy. Maybe I'll coordinate these by highlighting, you know, the yellow and the yellow. Okay, and the next thing we mentioned was 2 multiplied as a vertical stretch. So if you were to stretch something vertically, that means the y values are getting bigger. They're doubling. So here we're doubling the y values. Let's see. Let me erase the stupid graph that I found here. No. There we go. Yeah, we're talking about doubling the y values because that is what a vertical stretch does. Or sometimes it would triple. I mean, it depends on what this number is. Here we happen to have a 2. So we're multiplying by 2 or doubling. Double the y values. That's what's going on for that change. See, and highlight this so we see what's going on. And then the last thing we said was we're going to shift the graph up 3, which moves the y value up 3, which means you're going to add 3 to the y values. That was the last thing they did. Add 3 to the y values. Add 3. Alright, that's how you get it really precise. And then I think they plotted all those points and they obtained this yellow, this red graph here. So let's try to do that for the next example. Like I said, what you want to do is kind of take note of what's going on here from the inside out. So I'm gonna note changes to the x squared function from the inside out. Inside out. So like, okay, what's closest to x right now? Looks like the -3. So I'm going to look at the -3. Since that -3 is inside the function, that's going to be some kind of horizontal change. And I know when you're adding and subtracting, that just shifts you left or right. The minus sign inside the function actually moves you to the right, which is the opposite of what I would think. I'm going to move to the right graph. Right 3. Which, if you think about moving a point to the right 3, that adds 3 to the x values. X values, okay. And then if I look at the function a little more carefully, let's see. I've got the -3 going, or sorry, yeah. The x minus 3 squared. I think to me the next closest thing to x is this half. So I'm kind of, like I said, trying to work my way from the inside of the function out. The half, what does that do? Since that thing is outside the function, it's going to be a vertical change. So it's like that k times f of x, what we mentioned before. If the k is larger than 1, it's a vertical stretch, but if k is smaller than 1, it's a vertical shrink. Vertical shrink. by a factor of a half, which means you're going to be, I guess, multiplying, let's see, multiplying y values by a half. And I know it's y values because it's a vertical change. Vertical changes happen to the y values, horizontal changes happen to the x values. Okay, so we'll do that, and then the very last thing that I haven't mentioned about the function is the -2 at the end. Since that's outside the function, that's a vertical translation. That's going to be down shift. Yeah, sorry, I should say vertical shift down 2 units. And if I think about, okay, moving down 2 units, if I take a point and move it down 2 units, that changes the y value by subtracting 2 from the y value. Subtract 2 from the y value. Okay. So the idea is, let's start with the basic graph. Oops, you know what? I'm realizing they're saying here's x cubed. I'm sorry, this should be a cube as well. They should match. I'm sorry, so if you don't mind changing this to a third power. X cubed. Sorry about that. Because we want them to match. X cubed. I'm going to try to remember what that guy looks like. He looks something like this, you know, cute little guy. X cubed. But we want to do all these shifts to it. So what I have to do is kind of like what they did. They took the 3 basic points that are on the graph. -1, 1, 0, 0, 1, 1. And they did all these actions to them, the ones they described. And actually what's interesting is those points are also on this graph. Even though the last one was a parabola, the x squared graph, x cubed actually has three points as well. Wait, sorry. -1, 1, 0, 0, +1, 1. Yeah, so okay, if I were to move those guys, I'm going to try to highlight what I'm doing here. So how are those changing? I'm going to take all those and add 3 to their x values, okay, and then see what that looks like. I'm going to write those points right here. Okay, let me see. If I take the -1 and I add 3 to it, I'll get +2. If I take 0 and add 3 to it, I'll get +3. And right now I'm not changing the y values yet. They're staying the same because this is just a purely an x value change first. And now I'm adding 3 to the 1 and I'm going to get 4. Alright, now we're going to move on to some kind of y value change. The next thing we said we have to do is multiply the y values by a half. Okay, let's see how that looks. So we're going to, whatever happens, we're going to put those points right here. See how that looks. Okay. Okay. So if I multiply the first y value, which is 1, by a half, I'll just get a half. If I multiply the second y value by a half, 0 times a half is still 0, so that one doesn't change. The third point, though, 1 times a half is a half. Wait, oops, this is supposed to be a negative, I'm sorry. Oops. Hello. See that point right there? Should be 1, -1, I'm sorry. Hello. So maybe I'm losing my mind. That third point is a little different than the third point on the previous guy. 1, 1 is on the parabola, but 1, -1, or sorry, -1, 1 is on, damn it, I screwed it up even again. It's -1, 1. I put the negative on the wrong guy. Oh my gosh, I'm sorry. Losing it. Oh Lord. Oh no, I had that. Oh my God, I'm losing it. But it should be -1. Oh my God. Oh Lord, I'm sorry, you guys. Oh Lord. I screwed up this one. Oh my God. This one's screwed up. The top one. Oh my gosh. I'm sorry. You are probably going to want to kill me right now, but it should be -1, -1. Which, what did we do first? We added 3 to the x value. So that one didn't change. And then what did we do? Don't tell me. We were multiplying the y value by a half, right? Okay, so if I multiply that y value, same thing, by a half, I'm going to get -1/2. Alright. Did that even change? Wait, what did I do? Yeah? No. Yeah? No? Am I losing my mind? Yes. Probably. Oh, Lord. Alright, then there was one more change. If I can gather my thoughts enough, huh? I think I was okay all along. Oh my God. Alright, The last thing we're supposed to do is subtract 2 from the y value. Let's write those points here. And those should be the final points, and I should be able to plot this guy. Alright, if I subtract 2 from the first y value, I gotta think about that. -1/2 minus 2, I guess I could write -2 1/2. Yeah, whatever. And if I subtract 2 from the y value 0, I'll just get -2. The last guy, though, 1/2 minus 2 would be -1.5, I could write. All right, and those are our final points. Let me try to plot those guys, and I think that'll give us the graph we want here. We want 2, -2.5. So to the right 2, down 2.5, right about here. Okay, and then the next point is 3, -2, over 3 to the right, down 2. And then the last point is 4, so I'll go to the right 4, down 1.5. Wait, okay. Oh, 1.5's right here. Oh my god. Right there. Alright. So it's supposed to be a similar looking graph, but it kind of flattened out a little bit. And it moved to the right and down a little bit. Oh, so sorry, this stuff is very painful. It's probably the least fun part of math. So I just hope that this stuff that we kind of have to memorize for now and later on, it won't be so bad. I just hope it doesn't turn you off from math altogether. There's some hurdles you have to get over, and then math's actually pretty interesting and fun. You just have to get through these annoying things first. So, sorry about all the boring and tedious stuff, but I think we'll get to better stuff soon. So thanks for listening. I'll see you in the next video.